操他妈
这也被录进去了。Today my talk is on sound noise measurement of lithium aluminate strontium titanate electron waveguides. Correlated electron systems has many interesting properties, such as superconductivity and ferromagnetism. Non-electrics help us to design quantum devices, which enable us to investigate quantum simulation, quantum transport, and quantum sensing. Oxide heterostructures provide us with the opportunity to study these properties on non-electric devices. In our lab, we study lithium aluminum strontium titanate heterostructure. Both LAO and STO are insulating intrinsically, but when we put a thin layer of LAO on STO, a 2D electron gas forms at the interface. This 2D electron gas has a variety of interesting properties, such as superconductivity, which can be tuned by electric field, tunable spin orbit coupling, current inhomogeneity due to tetragonal domains, and electronically controlled ferromagnetism. Moreover, we notice electron pairing without superconductivity in our single electron transistor device. We can see here the magnetic field killed superconductivity, but the electron pairs survive at a magnetic field 1 order of magnitude larger than the upper critical field of superconductivity. So when we place just under 4 unit cells of LAO and STO, we can control the conductive and control the transition between conductive and insulating by conductive atomic force microscope lithography. In order to perform transport measurement, we deposit gold titanium electrodes to make contact with interface. Then we use conductive AFM to pattern our devices. When we sketch with positive voltage on our tip, it leaves protons on our surface, which attract electrons to the interface and thus make a certain area conducting. The nanowires we wrote can be as thin as 2 nanometers. And when we sketch with a negative voltage, it can erase the device, which allows us to make barriers on our device. This whole process does not modify the crystal structure of LAO and STO and can be repeated as many times as you want. We employ this conductive AFM technique to pattern 1D electron waveguide on our samples. So the main channel length is around 1 micron, and we first write with positive voltage and repeat with 2 dips in our voltage function to make these 2 highly transparent barriers, which isolate the waveguide from source and drain and allow it to be tuned by SiGate and make it tunable by SiGate. So this is the conductance of our waveguide device as a function of SiGate voltage for a sequence of magnetic field from 0 Tesla to 9 Tesla. We can see clear steps of E square over H, and we attribute the conductance plateaus to Landau quantization, for which the conductance is determined by available quantum channels, and the subband structure can be revealed by the transconductance dg over d mu data as a function of chemical potential mu and magnetic field B. The highlight means the crossover from one plateau to another. And although the single non-interacting band model can explain most of the data we got, there's also some devices which show strong electron pairing. You can see here the conductance jump is 2e square over h, and when we look at the transconductance data, you can see electron pairs survive at a field up to 11 Tesla, and some other devices shows this avoid crossing and reentrant pairing in their transconductance. We attribute these features to strong attractive electron-electron correlation. And so how do we decide the electron states without sweeping magnetic field and SiGate? So one of the ways is sound noise measurement. So sound noise is the current fluctuation due to due to the granularity of charge carriers. It offers a way to measure the charge per charge carrier heads. And Schottky first discovered the strong noise of a vacuum diode. Because the tunneling process is a full Poisson process, the current noise spectral density should be 2EI, and the final factor should be 1. And in our waveguides, when electrons are paired together, the conductance should be 2 square over h times the summation of the transmission probabilities of each quantum channel. And this is our shell noise, the experience for the shell noise spectral density, and this is the final factor. So, but when the paired mode splits into two independent modes, the conductance remain the same, but the shell noise and final factor reduced to 1/2. So we can do two kinds of experiments. We can first vary the transmission probabilities of our quantum channels by Seagate, and we should expect to see noise maximum whenever the transmission of the uppermost connecting channel is 1/2. And secondly, we can change our source drain voltage, and we expect to see double slope in the paired regime. We usually expect in the paired regime we should see the noise have double slope against the source drain voltage compared to the unpaired regime. So this is the data previously acquired by Reznikov group on a quantum point contact. You can see the noise peaks appear when the conductance is between two plateaus. And similarly, in our waveguide, we should see peaks in our noise spectral density when the transmission probability is half integer. And this is the data previously observed in a normal metal superconductor junction. We can see Cooper pairs generate double the Poisson noise. Similarly, in our device, we should expect to see doubled noise when the electrons enter the paired regime. So this is our experimental setup. We source a low frequency voltage, and for the conductance measurement, we source a low frequency current, and we do a lock-in measurement on the voltage drop across our devices. And for the noise measurement, we connect two low temperature amplifiers to the two ends of our device, and we connect their output to a differential amplifier, and there's also another stage of room temperature amplifier. So after the bandpass filter, the Schottky diode can convert the voltage fluctuation to a DC output, and we also do a lock-in measurement here. So this is the data we got. So we can tune the conductance of our device with Seagate, but because the temperature in the mixing chamber is high due to the coax cables connected to the amplifiers at 4K stage, so we cannot see any conductance plateaus, and we cannot see any dependence on magnetic field either. On the right is the noise intensity data. So it's a function of source drain voltage for a sequence of different Seagates. We can see it increase with our sourcing current, but there's no dependence on Seagate. We think that's also due to the high temperature in our mixing chamber. So for the next steps, we can replace the current coaxial cables with superconducting coaxes to reduce the temperature in our mixing chamber, and we can add bias tees to reduce the noise going into the measurement lines, and we can also add a LCR resonator circuit to make the impedance matching, and last but not least, we can do a whole gain calibration of the amplification system. So in conclusion, there's strong electron correlation in the 2D electron gas at the LAO-STO interface, and we can study the mechanics of this electron correlation by performing shell noise measurement. 说的不是我，他妈舌头老他妈在这。